Hello, dear students. This is your professor Lázaro Pino. Today we are having a presentation for Chapter 15, Chemical Kinetics. In the Chapter 15, we are going to see an introduction to kinetics, expressing the rate of a reaction, rate laws, concentration changes over the time, the activation energy and temperature, and reaction mechanism and catalysis. Introduction to kinetics. Kinetics of a reaction are influenced by number one, mechanism is the manner in which a reaction occurs. Number two, activation barrier is the energy barrier that must be overcome to convert reactants to products. Number three, concentration of the species present. And number four, temperature at which the reaction occurs. Collision theory of reaction rates. A reaction occurs when three conditions are met. Number one, reaction species collide. Number two, collision has enough energy to overcome the activation barrier. What does it mean? That even though two species collide, if the collision has not enough energy to overcome the activation barrier, the reaction is not going to happen. And number three, reacting species collide in an orientation that allows the necessary bond breaking and bond forming needed to transform reactants to products to occur. So it is very important the orientation of the molecules during the collision. When more collision between reacting species occur, the reaction will proceed faster. For a reaction to occur as a result of a specific collision, the collision must have enough energy to overcome the activation barriers, as I told you before. Molecules in a sample at a given temperature have a Boltzman distribution of molecular speeds and energy, but only a small portion of the molecules will have enough energy for a reaction to occur successfully. As the temperature increases, the number of molecules with enough energy to react increases. Here you can see how when we have a higher temperature, as you can see in this graph, the activation energy, the barrier, is lower than when the temperature is lower. And in this case, look at this. For a lower temperature, only a small molecule has enough energy to give the products. But when the temperature is higher and this barrier is smaller, a higher number of molecules have enough energy to give the products. Look at here how these molecules have a minimum energy required to react at a higher temperature. Overcoming activation energy. Reactivity also depends on the magnitude of energy barrier that needs to be overcome. More reactant molecules undergo reaction when there is a smaller activation barrier. It's the same action. Suppose that I put a big bench and I tell you, make a line and try to jump the bench. Well, most of you are not going to jump because it's too high for you. But if I put a smaller bench, most of you will jump over the bench because is the same way. The activation energy, the energy that is necessary to get the products or to undergo the reaction is smaller. And so the reaction will go faster. Here you can see how with a large activation energy, a smaller number of molecules have enough energy to get to overcome the barrier. But when the activation energy is smaller, a big number of molecules can have the energy or have enough energy to overcome or undergo the reaction. Molecular orientation. Orientation must permit necessary bond breaking and bond forming needed to transform reactant to products. When complex and larger molecules react with a specific reaction site, a small fraction of collision can leak the products. Why? Because only the collision can happen in one side of the molecule to break this bond and to produce new bonds and new products, of course. You can see here in this molecule, if chloride collide in this site, in the center carbon, the reaction will happen and you will get a chloromethyl from methane. That's a reaction that is very difficult to produce and require very high energy to be produced. But if chloride collide in one of these carbons in the outer part of the molecule, there is no reaction at all. Then it's very important the molecular orientation to permit that the bonds can be broken and new bonds can be made. Reaction rate. Here we have that the reaction that produces from A two molecules of B can be expressed by this expression. As A is the reactant, the concentration of A will be reduced over the time. So this will be, the delta will be a negative number. In order to convert this into a positive number, we put a negative sign. What is the meaning of this sign? It means that the reactant will lower the concentration or through the time. So the rate of the reaction can be expressed by delta concentration of A divided by delta T. That is the change of time. In other words, concentration of A at time 2 minus concentration of A at time 1 divided by time 2 minus time 1 with a negative sign because it's a reactant is the expression for the rate of the reaction. This is very important because you are going to get the expression of the rate of the reaction at the beginning of a reaction, and you are going to use this expression. So the speed of a reaction progress can be calculated using this ratio, the change of concentration over the change of time. Since A decreases over the time, we make it negative. So the reaction rate is defined as the negative of the change in concentration over the change of time. This uh, makes possible that this number will be a positive one. Average reaction rate, as two molecules of B are produced when each molecule of A is consumed, the rate of the formation of A is twice the rate of the consumption of B. So you can see how B increases over the time because the products will increase the concentration when the time goes by. And here you can see how the concentration of the reactant decreases when the time is increased. The average reaction rate can be expressed by delta concentration over delta time. So the rate will be the concentration of B minus of the concentration of B at different times divided by the change of the time. As it is equal to 2 times the change of the concentration of A through the time, we can express this by putting a 2 into here, and then this expression will be equal to this one. You can use this or this expression to express the rate of the reaction. And here you have the general expression. So here we have an example. Calculate the average rate of disappearance from concentration time data. And here you have a table, you have the chemical reaction, that is the decomposition of hydrogen peroxide by a diluted or a dilute sodium hydroxide solution at 20 Celsius degree. The question is, determine the average rate of disappearance of a reactant over a given period of time. You're given the balanced chemical equation, and also you have the concentration at different times. What you're going to do? Okay, you take um, for example, you can say the temperature, how will be the change or the average rate from 0 to 434 minutes. And then you see here the corresponding concentration. Then you put the concentration, the final concentration minus the initial concentration, divided by the final time minus the initial time, and you do the calculation, and here you have the answer. Of course, the units for the rate are molar divided minute. Molar divided minute, or you can express it in second, depends on the rate of a reaction. Here you have the reaction stoichiometry. Remember, directly related to the relative rate at which reactants are consumed and products are formed is the rate of appearance and the rate of disappearance. Appear, the product, disappear the reactant. And that's why this negative sign here. As two molecules of B are produced for each molecule of A consumed, the rate of formation of B is twice the rate of the consumption of A. So, obtained from change in concentration of a reactant or product over a defined time interval, you have delta Y, delta X equal to delta concentration over delta time. So what you are going to do, you can use the change of a concentration of a products over the time, or the change of the concentration of a reactant two times, by the way, because you produce, remember as I told you before, the formation of B is twice the rate of consumption of A. So you have to put a 2 in front of the consumption of A. Here you have an example. You can stop the video at any time and look at this. In this question, you are asked to determine the average rate of disappearance of a reactant over the given period of time. Then you use the formula, you use the corresponding two concentration and two times, the corresponding times. You plug them into the formula and you get the average rate of disappearance. Reaction stoichiometry. In this case, directly related to the relative rate at which reactants are consumed, the products are formed. So you have here that the number you are going to get for the rate if you use the appearance of B or the rate for disappearance of A, the number you will get will be the same. Okay, in this case, you can see how at certain time you will have an amount of A and amount of B at the same time because A disappears while B appears. The reaction, the A plus B equal to C plus D, a general reaction, we can express the reaction, the reaction by a rate by this expression. As A and B are reactants, you put a negative sign. And then this coefficient that is in front of both substances are used to divide the expression of change of the concentration divided by the time. The same here, but with negative signs because they are reactants, then this is equal to this, and is equal to this expression for disappearance of C and disappearance of D, always putting in front the inverse of the coefficient in the reaction, in the balanced chemical equation. Remember, the products, the rate will be positive because the concentration of the reactant increases over the time, when the time increases, while the concentration of the reactant decreases when the time increases. Here you can see an expression of the speed of a reaction. Look, here you have how the concentration of this reactant decreases from time zero to time equal to 6 hours. The instantaneous reaction rate is determined as the tangent line to the curve that expresses the change of the concentration during the change of the time. Here you can see that at 2 minutes or 2 seconds, the slope to to the product curve to the reactant curve at this time, the tangent uh, will give you the slope of this reaction, and this is the rate, the instantaneous rate at this time. Same thing here for the product curve. The slope at 2 seconds is this number, and then you have the rate of the reaction. Then, in conclusion, the instantaneous rate for a reactant or a product will be the tangent at at certain time in the curve. Then at this time you get the tangent here and the tangent here, and this will give you the instantaneous rate. Okay, the rate of a reaction at the beginning of a reaction is then when? When the time is 0. Then you get this when the time is 0. Then here, time is 0. You put the tangent and you get the instantaneous rate or initial rate. And the same thing here, at time 0, you get the tangent in this point, and you get the instantaneous or initial rate. The rate describes a chemical reaction. Then we can use instantaneous rate to express the reaction, to describe the reaction. You can see how at the beginning of the reaction, the rate is a very big number for the reactants, and at the end is a very small number because the reaction goes slower. The same thing, at the end the reaction goes very slow, and at this time the increase of the rate will be almost constant as the time increases. The rate laws show the quantitative relationship between the reaction rate and the concentration of the reactant. You can see that in general, here we have a general reaction where A plus B produces products. Always we work with the concentration of the reactants. As you could see, the numbers that we are going to get using the reactant or the products will be the same. So we are going to use the concentration, the change of the concentration of the reactant to express the rate of the reaction. So in this case, the rate will be directly proportional to a constant, the constant of the reaction, times the concentration of A raised to X, times the concentration of B uh, uh, um, with the exponent Y, and times the concentration of C with the exponent C. X, Y, and C are known as order of the reaction. Then the order of this reaction is X. The order of this reaction for this reactant is Y, and the order of the reaction for this reactant C is Z. Each concentration is expressed with an order. That is the exponent, as I told you before. The order can be 0, an integer, or a fractional number. When the order of a reaction is 1, we say that is first order. No order is written in this case. We don't put the 1. When you don't see an exponent, is because it's first order. The rate constant K converts the concentration expression into the unit of the rate. That is molar times second inverse. The concentration of a reaction for this reactant will in aqueous solution will be equal to this product in aqueous solution. This is this reaction is the decomposition of this compound. This compound, the name of this compound, by the way, is urea. So, the rate of the reaction will be the concentration of this reactant raised to the second. Here we have K, that is the rate constant for the reaction. 2 is the order of the reaction respect to this reactant. In this case, is second order. And this is the concentration of this reactant. The rate constant K is proportionally constant that relates rate and concentration. Then K is used to relate rate and concentration. It is reported at the temperature at which it is measured. So the temperature is very important in kinetics, because the same reaction can be slower or faster according with the temperature. Then every rate is expressed at certain temperature. Also contains information about the energetics and collision efficiency of the reaction. The reaction constant is equal to in this case, to or is equal to the this expression m if x and y are equal to 1, then k has units of second inverse. And if x plus y has an exponent of 2, k units are molarity inverse times second inverse. Remember that in a few words, it could be simplified by saying that the units of the constant in the rate expression are used to convert always the rate into molar per second. So if the reaction is first order or second order, the units will be different to get this result where K will be molar over second. Included in the rate law and calculated in, we have the moles per liter of aqueous species, the pressure units for gases. In solution, we use moles per liter, but in gases, we use, instead of concentration, pressure. Not all participating species will appear in the rate law. Example, catalyst doesn't take part of the reaction, so they won't appear in the expression of the concentration of the rate of the reaction. Sorry, species that do not appear in the overall reaction can appear in the rate law. What is the reaction order? Expresses the order of the reaction with respect to reactant and shows the effect of reacting species on the rate of the reaction. The exponents x, y, and z are known as order of the reaction, and they are determined from experiment, not stoichiometric coefficients, as I showed you before. Let's see. The reaction order could be 0, first order, or second order. In each case, the rate law has a different expression. The common reaction orders are 0, first, and second. The overall order is the sum of the individual reaction orders. For example, for this reaction, you add x plus y plus z, and you get the overall reaction order. Here you have examples of laws. For this reaction, the rate is equal to K times the concentration of nitrogen pentoxide. This is an expression of first order because here, even though you don't put the 1, you consider a 1 in here. Here is the second order, and here is the third order. Second order for nitrogen monoxide, and first order for oxygen, and third order for all the reaction. Let's see what is the method of initial rate. This is very important because it's the one that you are going to use at the beginning of the experiment of the decomposition of the hydrogen peroxide by potassium iodide in the lab. The reaction is repeated multiple times. Each experiment will have a different set of initial concentration for the reactant. Initial rates is measured from each experiment. Result is used to determine order of the reaction. Here you have some examples that we have seen before. The overall order of the reaction, as I told you, is the sum of the different coefficients. The order of the reaction expresses the order with respect to each reactant. And it shows the effect of reacting species on the rate of the reaction, indicated by the exponents as we have seen before. Remember, this exponent doesn't come from the stoichiometric expression of the reaction. Here we have an example of determining the rate law using the method of initial rates. In this table, here you have the chemical equation, and here you have how you changes the concentration of each reactant, and you get the initial rate for each concentration. Of course, in this kind of experiment, the temperature remains constant. In this case is 1280 Celsius degree. So look at this. In this case, you change the concentration of hydrogen. And you observe how the initial rate changes. As you increase the hydrogen, the rate of the initial rate of a reaction also increases. The rate law for the reaction is given by the rate times the constant of equilibrium, the constant of a rate of a reaction times the product of the concentration rates to the orders of the reaction for each species. You take the ratios of the rates of trials 3 and 1, as you can see in this expression, and then plugging in the values from the data, you get this. So you cancel the constant of equilibrium. You cancel this concentration because it's the same. And then at the end, what you have, that the rate of the reactions are equal to the change of a concentration of this species raised to y. So you divide both, and you observe that in order to get, when you divide this to this, you have a 2, and then is 2 to y. In order that this could be equal to 2, y must be 1. Let me stop into here because it could be confusing. What you have to? You have plugged the different data in the expression of the constant of the rate of a reaction. Then you have, let me go back in order you can understand. You're going to take the rate for trial 3 and trial 1, and you will plug here the concentration of the two reactants. You have all these in this table. Then you have the concentrations and you have the initial rate. Then you plug everything in the corresponding place. As K will be equal, you cancel up both. And the same thing with the concentration of this reactant. Then at the end will be, everything will be this equal to this. You divide and you get that is 2. 2 raised to y. How can you get How can you make that 2 that you obtain by this division will be equal to this 2 raised to y? Only can happen when y is 1. So, using this method, you can say that y, the exponent, is equal to 1. Then the reaction is first order for this reactant. And then you put a 1 over the concentration of hydrogen. But you don't have still x. What we do then? Oh, then we take this expression and you plug into here the two trials where you change the concentration of nitrogen monoxide. They are here, and you take the corresponding rate of the reaction, and you see that the concentration of the other reactant is this. You knew that the order of this reactant is 1, then you don't put the 1 in here. But you want to determine x. Then you divide this number by this number and you get 24. So, in order to, when you divide 2 divided by 1 is 2, of course, raised to y, to x. Then, when x, 8, sorry, when 8 is equal to 2 to x, when x is equal to 3, because 2 raised to the third power is equal to 8. This way, you determine um, the number 3, that is the order of this reactant of nitrogen monoxide in this reaction. So, you have that the total you integrating the rates of the laws, the mathematical equation that can be derived to show the relationship between the concentration of a reactant and the time are used to uh, uh, for reaction that involve a single reactant, but derived by integration of a rate law uh, is here. If a reaction is a first order, then you say that the concentration of A at T is equal to the concentration of A minus K, that is a constant, times the time. In the case of the first order, the expression is this. In the case of the second order, the expression is this one. You can stop the video at any time and take a look over the expression. I didn't go over the calculation of the different expressions, only I show you a method to calculate these expressions. I don't pretend you to learn it by how to do this procedure, but I want you to know the general procedure to get the order of the reaction. Here you have an example where you can apply what we learned before. This is you can stop the video and you can take a look of this In this case, you are asked to calculate the concentration of a reactant after a given period of time. What is given? Oh, the balanced chemical equation, the order of the reaction with respect to the reactant, the rate constant for the reaction, the initial concentration of the reactant at a period of time, and then you apply everything in the formula and you get the, the concentration of the reactant after certain period of time. Okay, here you have another example. You can stop the video at any time. You can study this. It's the same thing, the same procedure, but you can get more practice by studying this example. And here we have another example of use of integrated load to determine the rate. The graphical method, and pay attention to this to determine the reaction order, supposed to follow these steps. First, collect the concentration time data for the reaction at certain temperature. Remember, always as at a constant temperature. You plot the concentration time data in three different ways. You can express concentration versus time, natural log of the concentration versus time, or inverse of the concentration versus time, and then you will see if the order of a reaction is 0, 2, or 1 or 2. If one of the plots shows that the data falls on a straight line, then you said the reaction is 0 order with respect to the reactant. If the concentration versus time plot is linear, the reaction is first order respect to the reactant if the natural log of the concentration versus time plots is linear. If a reaction is second order with respect to the reactant, then the inverse of the concentration versus time give you a linear curve. Here you have examples of the three cases for a reaction order 0, for a reaction order first, and for a second reaction order. Here you have another examples of how to use the graphical method. You have here the table, and then you make the graph. Okay, here the line that you obtain is not a line. So you decided that this is not the order of a reaction. In this case, oh, you get a straight line. Then this is the order of the reaction, and in this case also was not a straight line. So this is not the order of a reaction. Then you choose the case where you get a straight line. Here you have an example. Okay, reaction half-life. Account of time required for concentration of a reactant to fall to 1/2 of its initial value. The first order reaction half-life, the half-life in this case is independent of the initial concentration. What you get? Oh, you get a fraction of the reactant remaining at different half-lives of the reaction. Let's see here. You have the concentration time for the decomposition of hydrogen peroxide. Here, what you do, you use the time, and you have here the concentration in mole per liter. And then you get that one half life is 600 is at 650 minutes. So the expression is for this reaction is 1 over 2 the concentration at this point. And for a second half-life happens at 1,300 minutes, and then you get that is equal to 1 over 2 times 1 over 2 times the concentration, the initial concentration. Okay, here you have examples, and here we have another uh, uh, problem that you can stop the video. Here you have the the equation, the chemical equation. You have the times and you have the concentration of this reactant. What is the half-life of a reaction? What is the half-life of a reaction when the concentration of this, and what is the reaction first order, or if so, what is the rate constant for this reaction? Then what you have to do, you you have the concentration of this reactant is half into this to this over the first 166 minutes of a reaction. Therefore, the half-life when the concentration of this reactant is this number is 166. The concentration of this reactant is half to this to 130 times 10 to the third minus third molar. When other 166 minutes pass, then you get that the half-life is this number at 166. Then what will happen at this using this expression that 0.693, that is the value that is given, divided the constant of equilibrium. Remember that the log of 2, the reaction is considered of second order respect to this reactant. Then you say the log of 2 divided by the constant is 2 the half time. So you have the log of this number, you have to calculate K, and you have that the time is 166 minutes. Then you divide 0.693 by 166 minutes, and you get what? The constant of the rate of a reaction for this half time. In a radioactive decay, all radioactive isotopes decay by first order reactions. Concept is used in radioactive dating, not written in terms of concentration units, written in terms of either quantity of radioactive particles present or radioactivity of a sample. Here you have an example where you are asked to determine the mass of a radioactive isotope remaining after a given period of time. You are given what? The mass of the isotope that is originally present and the half-life of this isotope and the period of time that passes. So you plug everything into the formula and you get the constant for this expression. Then you go to, to the expression that relates the concentration of the isotope at different time, and you use the formula for, for this reaction order, and you can calculate what you're asked for to determine the mass of the radioactive isotope remaining after certain period of time. The activation barrier is very important because the energy that must be overcome for a reaction to proceed to form the products are required by all reactions. Changing the temperature affects ability to overcome this barrier. In other words, you can see here how this reaction goes into two steps. One, step two. In this case, you plug in the diagram of energy, the transition state, the energy that is required for the reaction to overcome the products. This is the initial energy of the reactants. If this reactant overcome this barrier for that is the energy for the transition state, they can give the products. In order for a reaction to proceed, the reactant must have enough energy to surmount a reaction barrier where the high energy transition state or activating complex is formed. This barrier is called activation energy. You can see here in this reaction where delta E, that is the difference of energy between reactants and products, is negative. So energy is released and the reaction is exothermic. In this case, the reactant must get the activation complex energy or activation energy to produce the product. In this case, well, you see that the reaction is endothermic. So in order that the products can be produced, you have to absorb energy, or the system absorb energy to give the product. The activation energy is required for each transition state, is always positive, and when the reactants are converted to products, the difference of energy between the reactant and the energy of activation complex are very important units. The overall energy change, delta E, can be either negative or positive according with if the process is endothermic absorbing energy or exothermic releasing energy. Here you have the Boltzman distribution, where you can plot of the molecular energy at different temperature. more molecules exceed the activation energy, as you can see, at higher temperature. And the opposite, when the temperature is uh, is lower, the number of molecules that can give the product is smaller, and and you have a very large activation energy. The activation energy, if two similar reactions with the same energy are run at the same temperature, the reaction with the larger energy will be slower. Okay, you have to determine what is the slower step of a reaction when the reaction is produced in different steps. Uh, and here you see when the temperature is increased, the rate of a reaction increases and the activation energy remains unchanged. Here you have an example of problem where you have the initial concentration of the reactants, you have the activation energy, and you have the progress of the reaction. You are asked to identify the activation energy for the reaction to determine whether the reaction is endothermic or exothermic, and you must calculate delta E. The Arrhenius equation is this one, where K is a constant, is a rate constant that we have seen before. A is a frequency factor. E is the base of the natural numbers, and ERA is the energy of activation, R the gas constant, and T the temperature, always in Kelvin. The Arrhenius equation have A. What is A? It's a frequency factor. It's a measure of the number of collisions that take place with the correct orientation during a reaction. And the expression E raised to minus ERA divided by RT is the fraction of collision that occur with sufficient energy to overcome the reaction barrier. As the activation energy increases, this number and the rate constant decrease. And the opposite, when the temperature increase, this number and the activation and the rate constant increase. What you do in this case, you take 2 points. K2 is the constant of the rate of a reaction at certain time, and here you have the constant of the rate of the reaction at other temperature, and then you multiply by this expression and by the inverse of the subtraction of the temperature 2 minus the inverse of the temperature 1. This can be used to calculate the rate constant for the reaction at different temperatures when the activation energy and the rate constant at other temperature are known. Or also can be can be used to determine the activation energy when the rate constant and two different temperatures are known. Here you have a problem. You can start the video and you can see the problem at any time. You have here the solution. This is very important because it's also part of the calculation you are supposed to have during the following uh, lab. Reaction mechanism. Well, we can say that a detailed molecular level description of the steps by which products are converted to reactant is the reaction mechanism. And it can happen in different steps. According with the steps, you can see that if a reaction goes in one step, two step, three steps, and according with that is unimolecular, bimolecular, or third molecular. Here you have an example of bond breaking step. In this case, is a unimolecular elementary step. Here you have the bond forming step. Here you have a concerted process where more than one chemical reactions occur at the same time. And here you have another example where you are asked to identify the molecularity of the elementary steps of a mechanism. In multi-step reaction, there are several species that do not appear in the overall equation. They are called intermediates. Is a chemical species formed in one step of a reaction mechanism and consumed in a later step. Here you have an example where of the decomposition of ozone. It can be step 1 unimolecular and step 2 is bimolecular. These are the mechanism of the reaction. So you can add both and you can see how the net ionic equation is obtained. Because oxygen is just an intermediate. You have here an example, you can stop the video, and you can use this. Here you have how the activation energy can, for a reaction that happens in two steps, can be expressed in different ways. In this case, step 1 has the highest energy. In this case, is the opposite. Step 1 has the lowest activation energy. And here we have the rate determining the steps in the slowest step in the reaction. It is very important to know what is the slowest step. When you do the calculation in the way we have seen before, you can observe that the slowest step controls the rate of a reaction and determine the rate low. So you have here an example of how calculate or identify the mechanism that is supported by experimental evidence. Here you have data, you plug into the formulas, and you can see which one is the order where the line that you will make during graphing is a straight line. There are more complicated, complex. You can read this. I sent you already the presentation, and you can stop into here and you can see how the dynamic equilibrium is attained when both the reverse and the forward reactions occur at a fast and at the same time. This is when we talk about equilibrium, when the reaction is going forward and is going backward at the same rate. Here you have an example. You can start the video. It is explained already, and here you have another example where you study the rate of a reaction and you replace the intermediate nitrogen dioxide in the rate law. Assume that the first step comes to equilibrium equate the forward K1 and the backward K minus 1 rates. Okay, we have different methods that can be used to determine the reaction mechanism. Here you have some of them. Detecting an intermediate using a spectroscopy, or you can use trapping experiments, or you can use the isotopic labeling. Okay, here you have the most important things. Please go over the presentation that is longer than my explanation. Study and see you soon.